Hi everybody. I wanted to go over one of the sample problems that the professor did in class as a review for the test if you guys needed it. We did a problem similar to this, but it was missing this resistor here. He said that he would probably add a resistor or maybe change the resistor sizes or the capacitor sizes for the test. But I just wanted to show you guys how to do it. It's really simple. It's not really any different than what we did in class. So the first thing we want to do is redraw the circuit to find our Rth across the capacitor. So I've drawn that here, replaced that with a open circuit between A and B, and I've taken the voltage source and shorted it out. Remember that voltage sources get shorted and current sources become open circuits. So to find RTH, which is what we're doing right here, we're going to follow this path from A to B. A goes through 10 and then 50, so that combination of course is 60. And then this path goes from 30, and then it can go through 20 or it can go through the short circuit, but since it's going to find its shortest path of least resistance, it's going to go across and around that 20 ohm resistor. Remember that any resistor that's in parallel with a short circuit, it's 0. Just remember that this node, this node, and this node, and this node are all exactly the same. I'm sorry, these two share and these two are shared nodes. So there is no source across that resistor. So what we have is 30 in parallel with 60. That winds up being 20 ohms. Now the next thing we need to do is find the voltage across that capacitor. So we need to redraw this circuit. There's 225. Goes through 20. Then we have a 30. Essentially we have A. That's where the capacitor was. 10. 50. There's B. And then back to there. Now, if this isn't really clear, one of the things I like to do is kind of draw this in a line. So there's our voltage source at 225. It comes here. We can give that a name. I like to keep with the alphabet. We can call that C. There's C. And it has two paths that it takes. It goes up and then through 30. And since this is basically a wire here, this A is actually right here, so we can go ahead and draw the A to make this easier to see once we're done. Then it goes through 10. Then it goes through 50. That all goes back to essentially B, and then to the other side of the voltage source. Now the other path that it takes from C goes through 20 and then ends at the other side of the voltage source, so we can do that, and then we wind up with 20. Now remember that when you have any components that are in parallel, each side sees exactly the same voltage. So this 20 ohm resistor sees 225 volts, and all of this sees 225 volts. Now to find AB, remember that VAB is equal to VA minus VB. If we look here, we can essentially move this B down to here, and this whole thing is basically 0 volts. Every one of these things shares the same end node, which is at 0. So VB is equal to 0. VA is going to be the voltage that goes through 10 and 50 ohms. So 10 and 50 ohms is shared with the 30 ohm resistor, so we can do a voltage divider. We have 225 times this whole thing here is 60, divided by 60 plus 30, which is 90, and we wind up with 150 volts. Now, if this sounds familiar, this is exactly the same voltage and the same resistance that we had in the problem in the class. This shows you that adding this resistor in parallel with this voltage source does little to the problem for the capacitor. So once we've done that, we can redraw the circuit in our Thevenin form. 150 volts. We have our R Thevenin, which is 20 ohms. Then our capacitor, which is 100 microfarads. The first thing to do once we have it in this form is we want to find tau, which is equal to RC, which gives us 20 times 100 times 10 to the minus 6, which gives us 2 milliseconds. The other thing is 1 over tau, which makes the equations easier, which is 500. So for your voltage, VC, it's equal to E, which is 150, times 1 minus E to the negative T, 500. Now we got this negative 500T because the problem is negative T over RC, and since we did this 1 over tau, we can move that part of it up and multiply it by negative T, which makes the problem easier to calculate, to put in your calculator and everything. For your current, IC is equal to E over R, which is 150 divided by 20, multiplied by E, again, to the negative T, 500. That's exactly the same. This is exactly the same reason this one. So it works for both sides, and you'll notice that essentially these formulas are opposite of each other, where you'll have initial current, and then it goes to 0, and then your voltage starts at 0 and goes to 150. Now, one of the things I did was I went ahead and run this through a simulator to try to show you guys what goes on, and I've got that here. Let me rearrange this so you guys can see it a little better. Well, it may have been. Let's just leave it that way then. So when I set this, I'll show you guys the voltage as it steps up here. The voltage climbs, and let's increase the simulator speed here. It's climbing. The current drops. So as the current's coming to 0, we're getting closer and closer to 150 volts. Maybe get closer. And we're almost basically at 0 current. So there you guys go. It shows you that it's 150 volts, and that we did the problem correctly. Let me know if you guys need anything else.